All right, let's say that we have some data and we want to model it. Well, at this point, we've talked about a lot of different functions that can be used to model data. So specifically the ones that we're going to look at are linear data. Linear data might have, a line as the shape. We're also going to look at exponential models. Exponential models are going to have this shape of data. Exponential functions, which you should be pretty comfortable with right now. We also sometimes are going to be looking at logarithmic data, which has this shape. And lastly, sometimes we're going to look at logistic growth. Remember that is new from this section. Logistic growth tends to look like this with an asymptote. And in this video, we're going to talk about what these all look like, when to use each one, and we're going to be using technology. You can do some of this by hand, but technology is pretty powerful. So we're going to use a website called GeoGebra, which is very similar to Desmos. Okay. So we're going to start by looking at an example from the book. Example 7. Does a linear, exponential, logarithmic, or logistic model best fit with these values in this table? Find the model and use a graph to check your choice. So we're going to use this link, which can be found at the bottom of this module in Canvas, a link to GeoGebra. GeoGebra Classic, specifically the spreadsheet part of it. It can be a little weird to work with, so you can also graph this by hand if you'd like. But the nice thing about using a computer is that you can just copy and paste this table, drag your mouse over the entire table, Control C, or you can right click to copy. Go over to GeoGebra Classic, Control V, or you can right click and hit paste. And now all of that data is over here. Again, you might have to click on here to move things over. The data is immediately on here. Now, we were told to graph this on a scatter plot. So in order to do that, we're only going to copy the numbers. So drag your mouse all over the numbers and hit this histogram up here. This histogram, we're going to look at the scatter plot one, 2-variable analysis. And now we've got a scatter plot. That's just one way of using technology to get this instead of graphing it by hand. Again, you might want to drag things around. GeoGebra is not super user-friendly. And this is what we have. All right. So we've graphed it. Excellent. What was the second part of this question? Second part of this question said, find the model. Oh, it didn't even tell us to graph it, but it's a good idea to graph it. That makes it easier. Find which one fits best. I can't read. Which one fits best? Find the model and then use a graph to check your choice. Okay, so let's look at this. Does this look linear? Well, it's kind of close to a line, but not quite, right? It's a little bendy, it's a little curvy. Does it look like exponential? Exponential should be growing or decaying in this fashion. It doesn't look exponential. Does it look logarithmic? Yeah, kind of. It could maybe be like part of a logistic growth. Like it kind of looks like the second part of the logistic growth too. So what we're going to do in this one, we can actually click down here for a regression model and see how each of these models looks. So click on this button, click linear, and that shows you a linear approximation here. This is actually really cool where they come up with this, and we're not going to talk about that. You could look at you type in exponential, and GeoGebra gets really angry with you. It says, "Come on, man, this isn't exponential. We're not even we can't even model this. This is not exponential." And logistic, all right, it doesn't know how to do that either. Oh, logarithmic. Yeah, that looks really good. Okay, so this is logarithmic data. And that's going to be our answer for this problem. Okay, so, you know, this is example 7 from the book. Let's call that part A of our example 9. I would try to be consistent with my numbering. So we're going to say this is logarithmic data. And what's our equation? It gives us our equation down here. So there's a little rounding error. It turns out that this is actually exactly just 2 ln x. But because there's some rounding error in our data, it doesn't give us something that's exactly equal to. But you could answer either way, 2 ln x, or you could type in exactly what you see down here. That's our answer for this problem. And the second thing I want to look at is just the try it number 6 from the book. It just basically asks the same thing. So again, I'm going to copy all this data down, Control C or right click. We're going to go over here. And here, again, GeoGebra sometimes does a little weird stuff. Let's move this over to the side, move this over to the side, and try pasting the data. So notice that something a little weird is happening. First off, it's rounding a little bit. Second off, it's not 1 should be right above the 3.3. It's not doing that either when we're copying it. Oh, it's because I copied it wrong. Let's start from the X. Now copy it in like this. And now it's correct, even though it's rounding a little bit. Highlight the data. Make a scatter plot. Drag these windows over. You can see it. Oh, yeah, this one's not going to be a logarithm. What do we think this one's going to be? It doesn't look like a line. Kind of looks like exponential growth here. So let's look at them. Line, yeah, that's not a good model. Log, that's certainly not a good model. Exponential, oh yeah, that looks real good. Logistic, it doesn't really know what to do with that. Even though it could be like the start of a logistic model, but there's not enough information for the data to give you a really good one. Okay. So this one is going to be exponential. And there's other ones too, like you could model this with a power. You can model this with a polynomial. You can even tell it what degree. 3rd degree polynomial looks pretty good. The higher the degree of the polynomial, actually the better it's going to get. Get a really high degree polynomial, you can get a really good one. There's some really interesting reasons on why that is. You can actually model anything with a polynomial as long as you're only looking at a certain interval and you have a high enough domain. Talked about a little bit in calculus, something called Taylor series. Anyway, here it wants an exponential model. Okay. And it's going to be about y equals 2e to the 1/2 x. There we go. If you really want to play with regression models, it's really fun to actually go up here, the show statistics, and specifically look at this bottom one. There's two numbers that you want to look at. R is what's known as a correlation coefficient, and it basically just is the closer to 1 this is, or the closer to -1, the better the data fits. Or this bottom one is called the sum of squared errors. And that is another way of the smaller this number, the closer to 0 this number is, the better. So you can see with a line, sum of squared errors is pretty big. And actually don't look at R. R is only for linear models. It's the correlation coefficient. It has to do with how correlated the data is. Anyway, look at the sum of squared errors. That tells you how far your line is or your model is from these points. So the bigger this number, the worse the model is. So this one's pretty bad. That's a big sum of squared errors for our information. Log, that's even worse. 13,000. Polynomial of degree 2. Oh, sorry, polynomial of degree 2. That's much better. It's not updating. That's a third degree polynomial is what it's showing me, not a second degree polynomial. All right, well, polynomial of degree 3 is pretty good. Sum of squared errors is 36. The exponential is basically exact. All right. That sum of squared errors is 0. That's a little bit outside of the scope of this class, but it's fun to play with. All right. Let's do one more. We touched on this a little bit in the first video, but I want to talk a little bit more about it. Change y equals 2.5 times 3.1 to the x into the form y equals a naught e to the kx. So again, this first form, this is ab to the x. We talked about this a lot in 6.1, whereas the bottom one is a naught e to the kx. These are both ways of us talking about exponential functions. B was that growth or decay factor, and k was our growth constant or decay constant. And just like we did in the first video, the way that we convert it is by saying, well, if I want 3.1 to be e. So I can write it with an e as long as I compensate with a natural log. Right? These things are the same because e and natural log are inverse functions. They cancel out. If I'm looking at 2.5 times 3.1 to the x, let's just replace that 3.1 with what it equals. E to the natural log of 3.1. And now just simplify. This becomes 2.5 e to the natural log of 3.1 times x. Or you can approximate that k value as well. Right? Natural log of 3.1. What would that be? About 1.1314. So you could also write an answer like this. E to the 1.1314x would also be okay. All right, and that's kind of what it's just doing for these ones. And you can go backwards too. You can go in the opposite direction. Let me know if you have any questions and enjoy this fun section. I like this section. I like this section a lot. Maybe too much, but it's great.